Okay, this is my solution for the problem that we did about Bernoulli's equation. Now this device is called a Venturi meter, and what it does is that it has a large section of pipe, a small section of pipe, and then a large section of pipe again. And what we said is that through the large section of pipe, which say has cross-sectional area big A, air travels with a certain speed, capital V. In the small area of pipe, we'll call that little a, the air travels then with a different speed, little v. Now, it's a bit misleading, I guess, here that I chose big V and little v, because it's actually little v that is greater than big V. And we said that's because the equation of continuity. And the equation of continuity says that you can write the area of one part of flow times the velocity of the flow, and that equals the area in a different part of the flow times the velocity in that different part of the flow. And what we said is this is like a conservation of mass. Conservation of mass for an incompressible fluid. And up to sort of the speed of sound-ish, air actually is, to a pretty good approximation, incompressible, and so we'll use this idea. So Bernoulli's equation then uses this idea and says, Bernoulli's equation basically says that the net work that's done on the fluid equals the change in the kinetic energy of the fluid. So it's really just the work-energy theorem, but this time for a continuous medium. So we can write it this way. We derived it in class, but I'll just write it now. And basically you take the work, force times the distance, and you can write it in terms of pressure and area. Instead, divide by the area and distance to get a volume. Okay, anyway, what we said is that in any one place, pressure 1 plus 1/2 rho V1 squared plus, now the work done by gravity, rho g y1, that has to equal P2 plus 1/2 rho V2 squared plus rho g y2. So basically what this says is that if you have different speeds, you have different pressures. If you have different heights, you also have different pressures. Now it's important to remember that in this problem, the fluid we're talking about, air, is all at the same height. So what's the point of the water? The point of the water in the tube is to give you an indication of what the pressures are at these points. Okay, so we said from the last class actually that the change in the pressure from one side to the other is equal to rho g, this time the difference in the depths of the water, which is now h. I want to remind you that no matter what the tube is shaped like, if the water looks like this, remember that at every point along this line, the pressure is constant, or I should say maybe not constant, uniform, the same everywhere. Okay, so that's why we only really need to think about the difference between the left side and the right side to tell us the difference in the pressures between the left side and the right side. Okay, so let's see what else we can do here. So, okay, instead of the delta pressures, so let's see which one has the highest pressure. Well, pressure increases as you go down in a fluid, so that means the pressure at this point in the fluid must be higher than the pressure in this point. And so if that's uniform pressure all the way across, the pressure on the left-hand side is greater than the pressure in the right-hand tube. Okay, so we can write this down. So we'll write the pressure on the left plus 1/2 rho. Now let's see, V is going to be, so first of all, this is rho of air, you want to remember that. And this is V left, so we'll write that as capital V squared. They're at the same y's, so we can subtract off rho gy from both sides. This has to be equal to the pressure on the right plus 1/2 rho of air little v squared. Okay, and so for example, if we want to solve for little v, we can use the continuity equation and substitute in, instead of big V, the ratio A over A V squared. Okay, and now the other thing I'm going to do is subtract off, so we're going to take P on the left side minus P on the right side, and that's equal to 1/2 rho air little v squared minus 1/2 rho air now big V squared. Okay, now I can substitute this in down here, and so I have the rho of water times G times H. And this is going to be 1/2 rho air times V squared times 1 minus little a over big A squared. So if we imagine that we were trying to solve for the speed of the air in the tube, I'm just going to solve this algebraically. 2 times rho of water GH divided by rho of air 1 minus the ratio of the areas squared, and then I'll take the square root of that, and that is really the answer. Of course, to find the other velocity, well, we just undo that substitution that we did, and we have that the ratio for the big velocity is simply that ratio again times V. And we can see by looking at it that in fact this big letter I chose is going to be the smaller velocity. And that's it.